Okay, I'll hand over to Jodie Clark. She works at the Centre for Process Innovation, and her topic for discussion is on high throughput formulation. Can robots formulate for you? So over to you, Jodie.
So hello everyone. I am.
Wait, we haven't got any.
Oh, sorry.
Hang on. I don't know if I've got you. I haven't got. I can't see any slides at the moment. Phil, are you?
I can share them if you like.
Yeah, plans for Jodie to share on.
Okay, sorry.
Sorry. Right. Sorry about that. Can everyone see? Right. So I'm Jodie Clark. I'm a senior research technician at CPI. So today I'm going to be telling you a little bit about high throughput and formulating on robots. I'll just be going over a little bit about me and what it is I do day to day, a little bit about CPI, telling you about the robot capability that we've got, and then some case studies of what we've done with them. So I started my science career at Teesside University. I studied for a degree in crime scene science and crime scene investigation. But I found that I enjoyed the lab work section of the course way more than I enjoyed the crime scene. So I decided to go into lab work instead of crime scene. So out of uni, I got a job working at ICL UK. It's a mine that's located in Bowlby on the North Yorkshire Moors. Whilst working here, the mine produces polyhalite and potash fertilizers for agriculture. And my job was to quality analyze the raw materials that we dug out of the ground and then the final products that we made. One thing that I really enjoyed about working here is that my boss was very, very safety orientated, and this is something that I've carried forward into my future roles. After that, I worked at Cameron's Brewery, which is a contract brewer in Hartlepool. My main role here was quality control analyst, which required me to test lagers and ales all the way from brewing to final product in kegs, casks and bottles, and all the stages of fermentation and maturation in between. This also included tests for any microbial contamination in our microlab. The brewery was a very, very busy workplace, so I had to learn to increase my efficiency and cope well under pressure. We also had to deal a lot with plant breakdowns regularly, so this is also something that's helped me very, very much in my current role. I then, in May 2019, moved to CPI. It's my first experience with formulation, having worked in the quality industry previously. I found it quite difficult to make that transition due to having worked previously with specifications I had to hit, and my role now is very sort of, there's no specifications. So I had no previous experience in automation or high throughput, which wasn't a problem with this role because it's very much about the attitude and the enthusiasm that you have for the job. So a little bit about CPI. CPI is a company that's currently based in the northeast of England with one location in Glasgow. We are a company that works with other companies that are big and small. We proof, prototype, develop and help scale up to make sure that every idea has a chance at market. I work within the formulation business unit of CPI. That's located in Sedgefield, and then picture of the building there. We in formulation work with a large number of different industry sectors, to name a few: inks, fast-moving consumer goods, batteries, food and drink, pretty much everything, to be fair. So a little bit about my specific role. A huge part of my job is workflow creation. So as I said, I work with the robots. And a workflow is literally us telling the robot step by step what we want it to do. There are a number of different things that you've got to consider when you're creating one of these. For example, it's a transfer of a customer's process. Is the order of addition important? Because the customer making the formulation, we might have to make it separately and differently on a robot. So we need to know what's important in terms of order of addition. You need to take into account the sample run size and whether or not anything's time critical. You also need to take into account any potential bottlenecks within your process. There's no point making a run of 30 samples if afterwards you're going to do some kind of post-formulation analysis that only does a run of 10 samples and the samples don't have a great shelf life. I'd like to point out that no project's the same. So every time we start a new project or a new experiment, we have to do the workflow entirely from scratch. It's a complete fresh start. Another thing that I do is a lot of preparation for our high throughput campaigns. They tend to be very, very front loaded. We have to do a lot of prep before we can even start formulating. It's definitely not a case of just press and go and walking away and let the robot get on with it. So we have to do what are called dispense parameters. So this is basically the method of telling the robot how to dispense each material that we do. Obviously, each material is different, therefore they all have different dispense parameters. It's about striking a balance between accuracy and speed. You can get a 500 milligram dispense exactly on the money, but if it takes 20 minutes to get there, then it's not a very good high throughput formulation. Each material in a formulation will need dispense parameters. So if you have a very complex formulation of 30, 40, however many components, this can be very time consuming. We also carry out a lot of process validation. This is normally part of scoping studies. This is basically us doing initial tests to make sure that a customer's process can be transferred to a robot. This can be things like mixing method comparisons, and some materials can be relatively problematic to dispense on robots. We try and get around this best we can. Examples of this is, say, a test for the effects of additives on different formulation. And there's no point jumping in all guns blazing and doing hundreds and hundreds and hundreds of samples for each additive if it turns out one of them doesn't work properly. So we can do small tests with, say, the number of additives. This one doesn't work, right, we'll remove that from the campaign and then carry on forward. Another huge part of my role is robot troubleshooting and maintenance. So robots being very complex can go very wrong, no matter how well they're set up. We can try and negate this with our experience and very, very thorough checks, but things do genuinely go wrong. It's all about being able to sort of roll with the punches and know how and when to fix something. So the benefits of high throughput. So the high throughput team work across a large amount of different industry sectors, especially even within the formulation business unit. Therefore, we have to be a jack of all trades. The bottom line of high throughput is to be able to explore a wider formulation space than with possible and conventional methods. Again, it's to be able to create and analyze samples quicker than a human could, but then again, it's not always this straightforward and easy. Projects that I've worked on with the robots tend to be about the optimization of formulations, tweaking them just to make a better formulation, or substituting a material out because it's too expensive or too hazardous is also things that we've done. This is a quick overview of the robots and the robot capability that we currently have at CPI. As you can see, we have 3 formulation robots and also 4 analysis type robots. I'll be talking about them in a little bit more detail now. So this is the 2 ChemSpeed systems that we have. The ChemSpeed Formax is the top larger picture and the ChemSpeed Swing is the bottom picture. These 2 robots have a large amount of dispensing capabilities. They can dispense different material types such as liquids, powders, granulated solids, high viscosity materials, things like hand cream and syrup, all the way up to Vaseline-like consistency. There's a large range of customizability on the bed. We need to decide what a project needs and how we're going to set the robot up. So you can move the racks back and forward around the bed or even in between the two platforms themselves. Sample size, we can make samples anywhere from well plate all the way up to about 100 mil. We can mix the samples with vortex shaken, homogenizer blades and stirrer blades. We also have the added bonus of being able to create formulations within the formulation vessels, which are in the bottom left-hand corner of the Formax picture. We have 12 of these, and they're essentially mini reactors. They can be heated and cooled, refluxed and condensed, mixed with 2 different types of blades. They're just really good for testing formulations. We also have the added bonus of an automated TA cup and bob rheometer. This is fully automated in the sense that you can have your samples taken to the rheometer, tested, and then have the cup and bob cleaned and dried, ready for your next sample, all without the need for manual intervention. These robots have been involved in a number of different projects whilst I've worked there, mostly for things like fast-moving consumer goods like shampoo, laundry detergent, things like that. And they're very, very good at these type of projects. But we've had a lot of battery application projects recently, and we found that they aren't quite as good as we needed them to be, and we had quite a lot of capability gaps. So we decided to commission a new robot from a company called Labman. This is the robot there. Quick overview, it's got 3 separate sections, the process robot, the dispensing robot, and the nano robot. It's 10 meters by 2 meters, so it's a huge beast. And like I say, we wanted to be able to use it in conjunction with the 2 chem speeds, but then also the existing Labman robots that we already had. So the next slide, as I've said there, it's unofficially called CP30, that's the name. And the video is about to play where it'll show you it being built. So the way that it fills the chem speed capability gaps is we wanted a non-invasive type of mixing. So we have an automated DAC mixer on the robot bed. It's able to run 3 samples at a time, and the speed is variable and programmable. We also wanted to be able to automate pendant drop samples, surface tension with pendant drop samples. It's an analysis type that's quite desirable, and we found that it was quite fiddly and hard to do. So we've automated that system. We also wanted it to be able to deal with low density powders, like I said, for battery applications. So we have the Quantos in the robot, which deals very, very well with that type of material. Inside the dispensing robot, there's also large and small syringe dispensers, large and small powder dispensers, tech hands for the low viscosity liquids, and agitated syringe dispensers for slurries and anything that's likely to sediment. A major plus point of this robot is that it can multitask, so you can have a number of different workflows running at once and have it doing a number of different tasks at once, which is something that the chem speeds don't do. As I said, we also have an automated glove box within it. This is really good for automated battery slurries formulation. We also decided in previous projects that we've had bottlenecks in the process for samples needing to be put in syringes for use on different robots. So for that reason, we wanted to try and negate that, and we had an automated syringe filler put in. It also helps if the sample's hazardous, so we don't have to do it ourselves. Next robot. So these are the 3 Labman robots that we already had: CPID, CPRS, and CPOC. CPID, which is the one on the far left, is an interactive drawdown system. So fully automated drawdowns can either be onto microscope slides or metal panels. We then cure them and take them forward to the next 2 robots, which CPRS is a resistivity measurement robot. It's, as I said, it measures the resistivity on the microscope slides from CPID. It has an automated Keyence surface profilometer and automated 4-point Jandl 4-point probe. CPOC, the last one, is an optical coatings robot. It tests Gauss colour analysis and surface profilometry of the metal panels. So case studies. The first case study that I'm going to talk about is a project called LeBed. So this project was to try and swap out the current industry standard of silver in printable inkjet inks and replace it with copper. Copper was picked due to its low cost and low environmental impact. A number of things had to be considered when formulating these inkjet inks. For example, are the particles likely to sediment? Will a homogeneous coating be produced? Will the viscosity be within the printable inkjet range? And will the ink dry during printing and block the nozzle? The project initially wanted to look at 12 solvents, but it was decided that this was too many due to it being hundreds and hundreds and hundreds of samples. So what we did is we did a design of experiment using principal component analysis. And we, so what this does is it groups the solvents for their like qualities. In this case, things like boiling point, vapor pressure, surface tension, viscosity, density, flash point, qualities like that. And then it was narrowed down to 5 solvents using this. The problems that we ran into on this project were that the copper slurry that we had to add to the inks was particularly difficult to dispense on the Formax robot, which at the time was the only option that we had. This was due to it needing to be constantly mixed while it was being aspirated. It would have been much, much easier had we had the new robot. It would have been a doddle. So when the samples were completed, they were analysed for rheology with our TA rheometer. We also analysed them for solids loading and drying times with a Netch Auto TGA, so an automated TGA machine. We also tested the stability of the inks, and again, we decided to test them for surface tension with a pen and drop technique. So a successful sample was deemed to be one that had both good stability and a nice uniform drying. If you look to the left, the pictures of the 2 samples, the one to the far left was an example of a successful sample. The solvents that were chosen for this were able to keep the copper slurry in suspension, whereas the sample to the right, the copper, just despite being mixed while it was added and mixed afterwards, just completely sedimented to the bottom of our formulation vessel. The solvents just weren't able to keep it in suspension. All results were then added into a jump software, which then suggested, based on the results, an optimum formulation, which we then prepared on the robot and retested. And the results that came out of the jump software were exactly how the ink behaved. The next case study was a battery solvent and solubility study. So the point of this campaign was to look at the effects and benefits of different solvents and different binders on battery slurries. Having had PCA be a very powerful tool in the last case study, we decided to use this once again. The graph in the pictures is an anonymized version of what we got out of that. So this narrowed the solvents down to 10 and the binders down to 10. So this left us with 392 samples to create. They were very easy to create on the robot, just a simple liquid and powder dispense into 20 ml vials. The samples were then able to be heated and mixed because some of them hadn't dissolved, which wasn't unusual. Not all the samples were able to be heated due to the boiling, the flash points, and the risk of sample evaporation in sealed vials. So anything that wasn't completely soluble after 80 degrees and heating was deemed to be an unsuccessful sample. Apart from solubility, successful samples were anything with the correct type of rheology we were looking for, so anything pretty much flowable at room temperature. So apart from rheology, we also tested these samples on the Auto2GA for just to clarify total dissolved binder content. So something that was good for me in this study is we did some method development on CPID, the drawdown robot. It's not made to draw down onto foils, but we tried to see if we could do it, which it turns out we can. The reason that we didn't carry this forward is, as you can see in the bottom picture, the copper drawdowns look very nice, but the aluminium foil ones that we tried didn't work. So this idea was ultimately abandoned, I'm afraid. It's a capability gap that we can look to fill in the future. And all data gleaned from the initial PCA is exactly how, so the solvents that were deemed to be good in the PCA were actually the solvents that proved best in the study. So in summary, robots can be a very powerful tool when used to formulate. They can make samples very quickly and are very repeatable. So yeah, thank you. If anybody's got any questions.
Yes, so we've got a couple of questions. We haven't got so much time, I'm afraid, but maybe if I could take, maybe that's okay. Well, if I can take one, kind of combine a couple of them. It's really a question of how much of the process can you actually automate? So it seems like when it comes to things like decision making, or when you need a kind of an expert eye on something like rheology measurement, how much can you really automate? You still need somebody.
So the automated rheology is completely automated as long as it's cup and bob. You can have the robot put your samples into the cup, and then that's taken via a robot arm in the bed to the rheometer, tested, and like I said, it'll remove it and dry and wash and dry the cup, the bob for you, and then move on to the next sample. So we try and have as minimal amount of manual intervention as we can. Obviously, like I said, things do go wrong. So we do intervene when we need to, but apart from that, most things we just program the robot, do all the prep that we need to do, and let it get on with it.
Thank you. Great. Thank you very much.